tyrosine kinase receptors that when they bind to a growth factor, they will dimerize, transphosphorylate, and when they transphosphorylate, they phosphorylate a series of proteins in the cytoplasm to activate the phosphorylation cascade. And one of the proteins that has been found to be very important in activating the cell cycle is the RAS-G protein. And I've talked about this before, it's a G protein because it's activated by binding to guanosine triphosphate. Hence it's called a G protein. The RAS-G protein is important because it activates at least 3 different pathways to activate the cell cycle, to activate cell growth, and can also activate cell movement. Okay? So the RAS-G protein is very important in normal cellular activity. It activates cell growth, it activates cellular proliferation, it can activate cell migration. This is particularly important, certainly in embryonic development and throughout your childhood years, in your growing and development. But, what happens if the RAS-G protein cannot hydrolyze its GTP to GTP? It can't hydrolyze its GTP to GDP and turn off. And if the RAS, and that's what happens. And let's go back to this first slide I was just talking about. If you have the proto-oncogene encoding the RAS protein, and there's a point mutation in the gene that encodes the RAS protein where the GTPase activity of RAS no longer functions. And that's what's been found in a lot of tumors. When you look at the gene that encodes the RAS protein, there's almost always a point mutation within the gene that encodes the RAS protein where the RAS protein can no longer hydrolyze guanosine triphosphate to guanosine diphosphate. When RAS hydrolyzes guanosine triphosphate to guanosine diphosphate, then the RAS protein shuts down. So almost in all tumors found, usually what you'll see is that the RAS protein, the gene that encodes the RAS protein, has sustained a point mutation where the GTPase activity of RAS no longer functions, and therefore the RAS protein remains constitutively active, hyperactive. It's constantly signaling into the cell to grow, to proliferate, and to migrate. And it does that by activating a series of pathways within the cell that result in activation of a whole series of different genes that will encode proteins involved in stimulating the cell cycle. And so consequently, if you have a mutated tyrosine kinase receptor or a mutated RAS protein, these are called tumor promoters. They're called tumor promoters because they drive the cell cycle. Okay? Does that make sense to you? Can I explain anything again? Is it clear? So again, anything that stimulates the cell cycle is called a tumor promoter. And so consequently, mutated tyrosine kinase receptors, like what we were just looking at here, or mutated RAS protein, these are all called tumor promoters because they drive or stimulate the cell cycle. There's a question? Question? We okay? All right. Can we move on? All right. Before I move on, I'm just going to stress again what happens when these proteins stimulate the cell cycle. What this starts out as is activation of a series of transcription factors that are going to activate a whole series of genes that will change the your normal cell into a cell that simply goes into proliferation. Okay? All right. Now I want to talk a little bit more about the checkpoint proteins. So again, first thing you have to have is you have to have mutations in the genes that encode proto-oncogenes so that now they turn into oncogenes and stimulate the cell signaling pathway and cellular proliferation. The second thing that has to happen for a tumor cell to develop is you have to have a failure of the checkpoint proteins. So the genes that encode the checkpoint proteins have to sustain mutations so that the checkpoint proteins are no longer working. And one of our most important checkpoint proteins is actually called P53. It's called P53. P53 is a transcription factor. P53 is a transcription factor. P53 activates expression of genes that encode DNA repair proteins. P53 activates expression of genes that will halt the cell cycle so that it can repair its damaged genes. And I'm going to say this again. And if a cell has sustained too much damage, then what P53 will do is it will activate genes that will activate the apoptotic pathway, and the cell will go into apoptosis or programmed cell death. Okay? So P53, we only have one P53 gene. We don't have any backups. So P53 is one of your most critical checkpoint proteins. Again, it's a transcription factor. What it does is it activates genes that encode DNA repair proteins. It activates genes that encode proteins that will halt the cell cycle so that the DNA can be repaired. And then, if the damage is too great, P53 will activate genes that encode proteins that will start the apoptotic pathway. Okay? So does P53 cause apoptosis directly? No. It's a transcription factor that activates genes that encode proteins that will do that. You'd be surprised at the number of people who say P53 repairs DNA, stops the cell cycle, and causes apoptosis. Not directly. It's a transcription factor, and that's why it's able to do so many critical things within the cell. It activates a whole series of genes that will help the cell to maintain the integrity of its genome. And that's what P53 does. It is a transcription factor that activates genes that allows for the cell to maintain the integrity of its genome. If P53 is not working, when you've been laying out in the sun and UV light is hitting the DNA or chromosomes in your skin cells, and in those skin cells, if there has been a mutation, if that mutation occurs actually in your P53 gene, what's going to happen? You're toast. Well, not really, because that's what you get, and let's go all the way back. That's your non-melanoma skin cancer. And if you're paying attention, you'll get that cancer removed, and you've got a good survival rate. But that's what happens. That's what happens when you have the development of skin cancer, is you've been laying out in the sun, and of course UV light from the sun damages the DNA in your chromosomes. And what's critical for repairing that DNA is P53. If you sustain too much damage in your chromosomes, P53 will make sure that that skin cell goes into apoptosis. But if the mutation just happens to hit your P53 gene, that's when that cell has the ability to actually develop into a tumor cell. Okay?
Should P53 like the UVA should P53 technically just sort of that P53 altogether, right?
What?
Technically, we will have the person who has P53
In that cell.
Oh,
In that cell. Yeah.
So can I have a tumor again at the same spot? No?
Well, if in your skin cell you sustain damage and your P53 is the gene that sustains the damage, so it's no longer functional, that cell then will have the ability to turn into a tumor cell. Okay? Just that cell.
Okay.
Okay, all right. And so P53 is one of the most critical checkpoint proteins for helping to sustain the integrity of your genome. And let's go back. All right, this G1 checkpoint here. Do you remember what the G1 checkpoint protein is? It's the retinoblastoma protein. It was identified. The retinoblastoma protein was identified because when the G1 checkpoint protein, which is the retinoblastoma protein, doesn't work, what will happen is you'll develop a childhood tumor called retinoblastoma that actually affects the developing retina and the developing eye. That seems to be the primary tissue where the tumor happens, and it's thought that one of the reasons why when this checkpoint protein, when the retinoblastoma protein is not functional, you have some backup genes for that. P53, we have no backup genes. We have one P53. So if you have a cell that sustains a mutation in P53, that cell's in trouble because it can't kick into apoptosis, right? Nope. All right. So let's take a look at our overall summary of what I've just talked about. So when you have a proto-oncogene that undergoes amplification or is overexpressed, where you have an excess amount of oncoproteins functioning in the cell cycle becomes overstimulated, and you have increased cell division. Also, on the other side of the picture, if you have a checkpoint protein such as P53 no longer functional, the cell cycle will not be inhibited, and both of these will result in increased cell division. And I have to stress to you that the more cells divide, you don't have time to slow down and activate their tissue-specific gene expression program. So the more cells are dividing, they simply don't have time to activate their tissue-specific gene expression program. And so that's one of the reasons why not only do tumors have large cell masses, the large cell masses don't act like normal tissue. They don't act like normal tissue, okay? They've lost their normal gene expression program. And instead, all they're doing is replicating over and over again. Does anybody have a question? Okay. So the effects of the mutations result in a loss of a regulatory protein, such as a checkpoint protein. There's no inhibition of the cell cycle. There's protein overexpression in your cell-stimulating proteins, either overexpression or you have a mutation so that the tyrosine kinase or the RAS protein is constitutively active, and you get cell cycle overstimulation. All of this results in increased cell division, loss of normal cell gene expression program, and that is when you have your tumor. And again, for a tumor to develop, not only do you have to have a proto-oncogene turn into an oncogene, but you have to also have loss of a regulatory protein. You have to have both things happen. A lot of what is known about the development of tumors has come from epidemiological studies on tissue that's been removed from patients undergoing colonoscopy. So most of you, your parents, once they hit 50 is when you have to go in for a baseline colonoscopy. And what's been found across the United States with all these 50-year-olds going in for their colonoscopy every 5 years is you start to develop a bank of data that describes the kinds of changes that are actually occurring in the genes that drive colorectal cancer. And so in your normal colon, the normal epithelial cells that line the colon. And one of the things that's been found for people who are going in for their colonoscopy and they have a polyp that's removed. And have you ever heard about your grandparents or parents talking about, oh, so-and-so had to have a polyp removed? No? Oh my God. Well, nobody wants to talk about it. All right. But nonetheless, oftentimes what happens when somebody goes in for their colonoscopy, there'll be a small benign growth called a polyp. And the gastroenterologists that are removing the polyp during the colonoscopy, they take a look at this tissue, and one of the things they find is that in polyps, one of the first things that's lost is a tumor suppressor gene called APC. APC stands for Adenomatous Polyposis coli. Adenomatous Polyposis coli. And what this does is it actually helps to constrain the cell cycle. And when there's a loss of the gene that encodes this tumor suppressor, all of a sudden you get overgrowth of the cells. So patients who have been going in for their colonoscopy regularly, and the polyp actually goes on to develop into a larger growth called an adenoma, what they found in this case is that not only has there been a loss of the tumor suppressor gene, Adenomatous Polyposis coli, but there's also been a couple of other losses. First, there has been a mutation in the RAS oncogene in this tissue, and they've also lost expression of another tumor suppressor. DCC stands for deleted in colon cancer. It's actually a receptor. And then patients who've really been remiss, and not only do they let the polyp go and develop into an adenoma, but this adenoma eventually will then develop into a malignant carcinoma. And by the time the polyp, which is benign, develops into a malignant carcinoma, what you have is a loss of P53. So first you have a couple of tumor suppressors that are lost, APC and ECC. You have an activation of RAS. You can actually have additional mutations such as mutations in certain tyrosine kinase receptors, but critical for the true development of a malignant tumor is the loss of P53. Okay? So that brings me to my next point, which is, what is the difference between benign and malignant? Anybody know?
It doesn't really affect the function.
Well, actually it can't. The difference between benign and malignant, benign stays where it is. Benign will stay where it is. Malignant, on the other hand, actually invades the surrounding tissue. The cancer cells get into the blood vessels and migrate to other parts of the body where they'll form secondary tumors. So I'm going to say this again. The difference between benign and malignant is benign. The benign tumor will remain in situ, or where it starts, whereas a malignant tumor, the tumor cells will invade the surrounding tissue. The tumor cells will migrate into the lymph or vasculature and migrate to other parts of the body where they'll establish secondary tumors. And that's called metastasis. That's called metastasis. Can a benign tumor kill you? Yes, it can. Yes, it can. If you have a tumor growing on your brain stem, and a surgeon doesn't dare go there, because if the tumor is inoperable, because it's actually growing near the nerves that are controlling your heartbeat and your respiration, is that going to kill you? Absolutely, absolutely. So benign tumors can be benign tumors depending on where they are, how big they are, what they're interfering with. Benign tumors absolutely can be deadly. They absolutely can be deadly. Okay, you all right with that? Not really? Not a happy situation. You just don't get tumors at all. That's your best bet. Okay. And so the metastatic tumor that I just described starts out as benign, and then what will happen is the tumor cells will actually start to invade surrounding tissue, and they do that by the tumor cells actually expressing proteins called metalloproteinases. Metalloproteinases are proteins secreted by the tumor cells that actually break down the extracellular matrix and allow for the tumor to invade surrounding tissue. And also, it allows for what we would call formation of blood vessels into the tumor. And this is critical. It's called angiogenesis, where new blood vessels will grow into a tumor. For a tumor to be able to grow and develop, this is the rate-limiting step. It actually has to be able to force the development of blood vessels into the tumor, or the tumor cells are going to become necrotic and die. Necrosis means cell death, and when you have blood vessels that can't get to the tumor tissue, then the tumor tissue will die. The tumor tissue will die. That's called necrosis. And so for a successful malignant tumor to develop, it has to be able to bring blood vessels into its vicinity. It has to shed cells into those blood vessels, or in the case of certain types of tumors like breast tumors, it can actually shed cells into the lymph. And again, send these cells all throughout the body to form a secondary tumor. Okay? All right. So what on earth is the primary means for treating tumors? The primary drugs that are used for treating tumors are drugs that are actually designed to stop cellular proliferation. To this day, most tumors are treated with either radiation therapy or chemotherapy, and in both cases, for both radiation therapy and chemotherapy, the target is some aspect of a rapidly dividing cell. Because if you recall when I talked about the cell cycle, most of the cells in our tissues are in G0, right? They're not in proliferation mode. They're actually going about the business of maintaining the organs and tissues. Cells that are constantly proliferating are the epithelial cells that line our gastrointestinal tract, as well as the epithelial cells in our hair follicles and our skin. And so consequently, when patients are treated for their tumor using chemotherapy or radiation therapy, the chemotherapy and the radiation therapy are targeting aspects of rapidly dividing cells. Hence, that's why patients who are on chemotherapy or getting radiation therapy experience nausea and hair loss, is because the chemotherapy is not only targeting their tumor cells, it's targeting their normal cells. And I will finish this and continue on Friday.